the speak. Yeah, welcome everyone to today's ASP seminar. Today's we features Chenxiao, are exponential speakers from Toyota Technology Institute at Chicago. His research interests include LM reasoning and machine learning series. Today he will talk about pencil, long thoughts with short memory. Let's welcome our speaker.
Okay, thank you for the invitation. Today I will share our recent work called Pencil Long Thoughts with Short Memory. This is collaborative work with Nathan Srebel, David McAllister, and Zhiyuan Li. Um, Chain of thought, as we all know, is most commonly used the reasoning paradigm used in most large language models. Instead of given the question, instead of giving the answer directly, chain of thought will prompt let the model to generate us a series of intermediate results before giving the answer. And recently there has been a lot of powerful language models such as O1 and O3, and this figure shows that this figure shows their performance of O series in a benchmark called ARC-AGI pub, which evaluates how well these models perform and how these models are close to AGI, and like as this figure shows, so where the x-axis is the cost per task and the y-axis is the performance or the score. As we can see, with more powerful models, they can think longer using more test time computes and get better performance or better score. Also, there are some reproductions of generating longer chain of thought in academia, like this paper S1 simple test at scaling. This figure shows that given more average thinking time or by generating more tokens, the accuracy can dramatically improve from like almost 0 to like 60% on, for example, AMI 24. And there are a series of theoretical results showing that given more test and computes, or by generating more intermediate steps, a longer chain of thought can empower transformers to solve more complicated tasks. Like, for example, there is a paper in 2024 showing that chain of thought is Turing complete. Like, if we allow it to generate an infinite amount of thoughts, or like giving it infinite time to compute, then it can solve any computable tasks. So this shows how powerful by inventing the chain of thought. Though chain of thought is great, it can significantly improve the performance of language models, but there are inherent limitations of it. For example, so how a chain of thought is implemented in language models, we use a base model like transformer or whatever other base models. We keep generating next tokens. This is called the autoregressive next token generation paradigm. Given the question, and we generate next token, and we append the next token to the current sequence. So we keep doing this iteratively until we get the answer. And like the intermediate thoughts here are kept in the context forever. We never erase thoughts. So if consider solving a very complicated task, then maybe the chain of thought would become very long, and there is no such mechanism like it will kept in the context, and there is no such mechanism of erasing it. It will cause many difficulty or challenges. For example, if the task is too complicated, for example, consider some like NP hard tasks where you might need, for example, exponential steps to solve it. It will cause out of memory, for example. It will, or even if it's not out of memory, it will exceed model's effective context windows. So like important information will be discarded in the context, and you will never be able to retrieve that. This will also introduce some like computational cost. For example, when the context is too long, or when the sequence is too long, the self-attention makes generating each new token much more expensive because of the quadratic complexity. And also, this might cause some low accuracy, as shown by some recent works. So even if the model can fit the whole context into their context window, and even if it can generate longer thoughts and using very large memory, some relevant information will become buried in this very long context. It will be very hard to retrieve those relevant information. But fortunately, we observed that most intermediate steps are erasable. Like, for example, consider this example in math. If we want to solve a theorem, prove a theorem, for example, there are infinitely many prime numbers. So how do we prove this? We might need to prove some lemmas. For example, here we might need this lemma every integer n greater than one has a prime p divisor. So, but to prove this theorem, but the proof of this lemma is no longer useful because if we know that this lemma is correct, because in the proof of this theorem, we only need the result of this lemma rather than the proof of this lemma. So here, the proof of the lemma is no longer useful when we generate the future thoughts for proving the theory. And this is generally true for in like those in LM's reasoning process. For example, there is an example in real-world deep-sequence R1 run, like answering a question. Your mother has four children, north, south, east. What's the first child's name? So initially, the model might try different strategies to answer this question. For example, here, the model might answer that the first child's name is West, but then it realized that maybe this is not true. Maybe it's a trick. Your mother's means you are the first child, so the answer might be your name rather than West. So, like by realizing that your previous strategy is wrong, and by exploring a new path, the previous thinking process is no longer useful and it does not need to be kept in the context. And more generally, the idea of erasing the thoughts or discarding the computation, discarding information stored in the memory is a fundamental idea in the history of computation. If you think of transformer as a computational model, one step of forward process of generating a new token, you can think of it as a one step of computation because it's essentially like doing some computations to generate one thought and keep store it in the memory. So there is an analogy between like if throughout this talk we will like the idea of thinking and the computation we will use them interchangeably. So think of the earliest computational models like Turing machine, which is proposed in 1936. Even the simplest computational model, it will rewrite. There is a tape to store the information, to store the intermediate computations, and the Turing machine will like move their head and rewrite symbols on the tape. It means that it will use the number of steps for computation might be larger than the actual space used for this computational model. And this idea is prevalent. The idea of erasing the computations or erasing the information is also very prevalent, like in modern computers. We store, for example, when running programs, we have a fixed size the memory and we store useful information in the memory. And when we no longer use it, it has some kind of, for example, garbage collection mechanisms to clean the memory. But nowadays, as we are the most prevalent, most powerful model we use here is like a transformer plus train of thought. We use train of thought. Train of thought is like a pen. It generates thoughts using the transformer-based model, and it never erases thoughts. It's fundamentally problematic because, like, if we think of the counterpart between Turing machine and modern compute, if we think of it as a computational model, it will prohibit it to scale to larger size the problems. When the size of the problem is not too large, it's not a problem. But if we want to solve more complicated problems and unleash its power, it's very problematic. So this is why we propose a new thought generation paradigm, which we call pencil. So pencil here is a shorthand of pencil enables context-efficient inference and learning. So as the name suggests, the fundamental idea of pencil is to improve the efficiency of language models and enable it to using limited resources to address more complicated problems, to make it generate longer thoughts without exploding the memory. So pencil, it can like as the name suggests, it can write and it can erase. So for the write part, it works just like chain of thought. It's an autoregressive next token generation paradigm. It just use a base model like transformer to keep generating the thoughts or keep generating the next tokens until we get the answer. But how do we do erase? So this is a question. There is no set previous ways how we can do this. So we take inspirations from functional programming. So like in the design of functional programming, we keep calling functions. So when we solve a problem, we define a function to do this, and when we find this problem itself is very hard to address, we will call another function to do some sub computations, and this will create some stack frames, and the memory the information used by this function is stored in this stack frame. And when the function returns, it will automatically eliminate the memory stored in that stack frame, and it will do it recursively until we get the final answer. And then when we get the final answer, the all memories like will be just erased, and we only get the answer itself. So this is how we this and our reduction rule and our erasing mechanism is inspired by functional programming. So how do we do this? We rely on a very simple reduction rule. So as shown in this slide. So here, C refers to the context, which is the subsequence. T here refers to the thoughts, like the intermediate reasoning steps generated for answering the question. And A refers to the answer. Here we introduce three special tokens, which is called call, sap, and return. And whenever the current sequence satisfies this pattern, it will trigger this reduction rule, and the reduction rule will discard the intermediate computations, will discard the solves, and also these three special tokens, and only keep the answer part. It will merge the answer back into the context. So Pencil will iteratively generate thoughts and triggers reduction until we get the answer. So consider a concrete example here. Here is a question or a prompt. A toy store put together party bags for a birthday. They made 3 blue bags with 5 toys each and 2 red bags with 4 toys each. How many toys were used in total? So this is a very simple arithmetic expression evaluation problem. So how would a pencil address this? It will realize that it can decompose this problem into sub-problems. For example, the first sub-problem is to calculate how many bags are there in like blue bags. So by calculating, so after some intermediate thoughts, it leads to the result there were 15 toys in all blue bags. And when we know the answer of this sub-problem, we only keep the answer of this sub-problem. So now we have the model has keeps generating until we get the return token. It will trigger the reduction rule. So how does the reduction rule work? It will find the last return special token, and it will find the last sub token before this return token. Then it will find the last call token before this sub token, and then it will trigger this reduction rule to eliminate the intermediate computations and only keep the answer to the sub-problem. There were 15 toys in all blue bags. So this is how one step of erasing work. And also it will keep doing this. Like there is another sub-problem, meaning how many toys are in red bags, and when it get the answer to the sub-problem, it will merge the results back. And now we know the answer of both sub-problems, and now we can address this problem itself. Now by simple addition, there were 24 toys we used in total. Then it will eliminate all the intermediate thoughts and only keep the answer part. There were 24 toys used in total. So the key part here, one thing important to notice here is that it can be done recursively, meaning that in the context part, the C part, the context part could include other special tokens. For example, it can include many call tokens, so that it can be it works just like you can call other functions recursively. As we will see later, this is important to ensuring the space efficiency. Otherwise, if you just call if it doesn't have this hierarchical structure, it doesn't work as well as the current design. So here is an animation of the entire process. Like it keeps generating, and when the current sequence met this satisfy this pattern, it will erase the thoughts until we get the answer. So here is a summary and comparing how chain salt works and how pencil works. Here is the prompt. And for chain salt, we will just generate the entire reasoning process until it gets the answer. But for pencil, it will only return the final answer. But there is a very long thinking process, which is what we call hidden COT, which is hidden from the user. This is just it works just like, for example, when we are using OpenAI A1 or A3, it will hide the intermediate thinking processes and only return the answer. So in this way, if we consider the maximal context length here, chain of thought is significantly larger than pencil. So to give a deeper understanding how efficient the pencil can be compared with chain of thought, let's consider another example, which is called the quantified Boolean formula. So the problem is like this. This is a Boolean formula, and we want to answer if there exists such a value assignment for x2 and for any value assignment for x1, the Boolean formula is true. So there is no, because this is a piece-based complete problem in like complexity theory, meaning that there is no efficient algorithms to solve it. So the most naive way to solve it is just by trying different value assignments for these two variables until we find the final answer. So how would the pencil do it? It will try, for example, try x2 equals 2 false and try x1 equals 2 false. And then by substituting these values into this Boolean formula, it knows the answer is false, which is just a it's just the answer to this sub question. And because it says for any value assignment for x1, and we already know that when x1 equals to false, the answer is false. So we know the answer to this sub problem is answer is false. So we merge the results back into the context, and we keep trying the value assignment for x2. We assume x2 is true, and like try x1, and we find that. For both value assignment for x1 is true or false, the answer is false. And we know that the final when x2 equals to true, the answer is false, because for both value assignments for x2, the answer is false. We know the final answer is false. So during so the idea here is that like it is trying to search different possibilities for these subproblems, and when it creates a search tree, and when a certain path doesn't work, it will eliminate the thought process of this entire path and only keep the answer that this path doesn't work, and we don't need to try this possibility in the following reasoning process. And in this way, for chain of thought, it will explore all the possibilities. The context length or the thinking process here is exponential to the size of the problem. So the size of the problem here is defined as the number of variables. For example, in this example, there are two variables, n equals to 2. And for pencil, because it maximally the context length won't exceed the depth of this tree. So the maximal context length is just linear to the size of the problem. So the gap between pencil and the chain of thought is exponential in this case, which is very significant. So here, because in previous example, the gap between train of thought and the pencil might not be so significant because the size of the problem is not too large. This is not a too complicated question. But as we scale to larger size of problems to solve more complicated tasks, the gap is much, much more significant. For example, when the size of the problem, when the number of variables is 10, the gap is like 0.004, which is very dramatic. And there is another problem, which is called the three set, which is just a special case of QBF. And as we can see here, the performance, the maximal context length gap between train of thought and the pencil is still very significant. So imagine here, we use this empty slide to address the QBF problem. And for chain of thought, it will generate this much like thoughts to solve this problem. But for pencil, it will only require this much thought. This is the context length used by pencil. So a follow-up question is like, how does pencil perform in real-world experiments? So we will answer this question in this chapter of the talk. So before introducing the results, we will first introduce the experimental setting here. How do we train pencil, and how does it behave during inference? So for training, it's very simple. It's just the key difference between train of thought and the pencil is just how the data is generated. For chain of thought, there is like as we know, it's just a very long sequence, and we train we compute the cross entropy loss on this very long sequence and train the train transformers. But for pencil, it will also include some special tokens. It will because of these special tokens, it will decompose this very long sequence uh, a pair of like shorter sequences, which is the reduced sequence and the new thoughts generated upon this reduced sequence. And there is a series of this reduced sequence and generated and the sequence after generation in this in the data set. This is how the data generation process is different for chain of thought and the pencil. Otherwise, all the training procedures for chain of thought and the pencil are identical. So here are the loss functions for chain of thought and the pencil. So for chain of thought, it will calculate the loss function on each next token based on the complete sequence, which is very long. But for pencil, it also computes the loss on each next token, but the loss function is calculated based on the reduced sequence rather than the complete sequence. And this is the reduced sequence length is is significantly smaller than the complete sequence. And for our setting, we train a very small transformer, like only with 24 million parameters and 2,000 context lengths from scratch. And during the inference, we can preserve the KV cache of the context part, and we only need to recompute the KV cache for the answer part. So the additional computational cost is to the recomputation for the KV cache of the answer part. But as we know, because the context length, the bottleneck is the context part, so the additional computational cost is neglectable here. So it but just because the context length because the complete sequence is significantly longer than the reduced sequence, so the overall computation for chain of thought is significantly larger than pencil, as we will show in the following experimental results. Here we compare the performance of chain of thought and pencil on 3-set and the QBF, these two toy examples as we mentioned earlier. So here n refers to the size of the problem, meaning the number of variables in the Boolean formula. And the baseline here is just a training the model to directly generate the answer rather than meaning that using no chain of thought. Here, as we can see from this table, when the size of the problem is not too large, both train of thought and the pencil can achieve almost perfect performance, which is significantly better than not using chain of thought. But when the size of problem becomes large, the performance of chain of thought degrades dramatically. It degrades from almost perfect to almost random guessing. 50% is just the accuracy of random guessing. So for pencil, the accuracy just it's always perfect. It means that using longer, this means that using fixed size the model using limited context window, pencil can solve significantly harder tasks than chain of thought. Also, we compare the chain of thought pencil is significantly more efficient than chain of thought, as we can see from this figure. This figure shows when we train chain of thought and the pencil, how does the performance evolve during the training process. And the first line of the figure shows the evolution of the accuracy, and the second line of the figure shows the evolution of the training loss. As we can see here, given the same number of iterations, meaning training on the same number of tokens or sequences, the performance, pencil converges to the optimal performance faster than chain of thought, and it's even more sample efficient, meaning that it can use less examples to achieve better performance. But as we mentioned earlier, because the prefix length for pencil is always significantly smaller than chain of thought, So another advantage here is the pencil for each sample or for each iteration, the compute used by pencil is significantly smaller than Chenxiao. So if we change the x-axis of the previous figure from number of iterations to the training flops, meaning that we restrict the amounts of compute for training the model, then the performance gap, the convergence speed gap between Chenxiao and pencil is even more significant, as we can show here. It converges significantly faster than Chenxiao. It shows how not only pencil can address more complicated problems, it also converges faster because as we can see here, both Chenxiao and pencil can converge to 100% performance, but pencil uses significantly less compute to do so. And let's consider a more complicated problem beyond just the reset and QBF, which is called Einstein's puzzle. So the problem works like this. The prompt consists of a set of constraints, and our goal is to fill this table. So there are, for example, in this example, in the table, there are 3 houses, and each house has a unique color, and the nationality of the people living in these houses are different, and these people kept different pets in these different houses. And now we don't know which the color of these houses, and we don't know the nationality of the people living in these houses. But based on these constraints, which gives clues of how, like for example, the greenhouse is immediately to the right of the one who keeps birds. So based on these constraints, we want the language model to infer the colors of these houses, the nationality, and the pets. So here the example here only has 3 categories, but for real world Einstein's puzzle, there are 5 categories, which is like there are dozens of constraints, which is a very complicated question. It's claimed that 98% of world's population cannot solve this problem. So this is like we want the model to fill this table and answer the question, who owns the fish? So here is how pencil solve this problem. We can consider each constraint as a subproblem. So by considering each constraint, we eliminate the impossibilities to fill in this table. So here we can by considering each constraint as a subproblem, and when we get the answer that what are the possibilities to fill in this table, and what values are impossible to fill in this table, we get the answer and then we can eliminate the intermediate thoughts to get this answer. So, and after considering all constraints, meaning that after we have solved all these subproblems, we will summarize the state changes, meaning that we know that we can summarize after considering all these constraints, what are the remaining possibilities to fill in this table. Now we can just erase all the previous thought processes and only know the answer part is just what are the remaining possibilities to fill in this table. This is like how we do summarize. This is like a way to summarize it. Then we can, because after these steps, we still don't know how to fill in these tables. For example, for the first house, there are 2 possibilities for the color. For example, it could be a red house, it could be a blue house. Then we can try for example, we can try if the first house, if the color is red, does it lead to the correct solution? And if it doesn't lead to the correct solution, we will just eliminate the reasoning process for this branch and only keep the answer that the first house can't be red. Then we know the answer is that the color of the first house is blue. So this is how we can comprehensively use pencil for different purposes and to address this very complicated problem. And one special usage we use here is doing summarization. So this is how we can do summarization here. The answer part here, T here refers to a very long thoughts, and the T prime here refers to the summarized thoughts. And here, the answer here includes a special token call, and this is how summarization works. This is the summarization here is inspired by tail recursion optimization in functional programming. For example, here in functional programming, the value returned by this function is calling another function. For example, here we want we write a code to address the factorial to compute the factorial of a certain number. It returns another it calls itself. So the returned value here is because it's calling another function. So here the answer is like another question. We are transforming one initially complicated question into a more simpler question. So this is how this is how the summarization works and the analogy, which is analogous to tail recursion optimization in functional programming. And this the reason I mentioned this so detailedly here because we might use this rule, this reduction rule, to prove the theorem in the following talk. Here is the performance on Einstein's puzzle. As we can see here, we evaluate the performance of Chenxiao and pencil on different sizes of the Einstein's puzzle. When the size of the puzzle is 5 by 5, where there are like 5 different categories, which is the most complicated variant of all different variant. So for pencil, it can achieve almost a perfect performance, but chain of thought the performance is like 25, which is close to random guessing because even if you just random guess, the performance is 20%. I also want to mention that for like this is a very complicated problem. Even GPT-4 struggles with if you consider using ChatGPT to solve it. It won't solve it correctly, but we are just using a very small transformer, as we mentioned earlier. It's just 25 million parameters. So we can show that by using Pencil, it can solve problems that even very powerful language model, large language models cannot solve. So the reason is because without erasing the thoughts, the number of tokens generated by train of thought is like 150,000 tokens. But for Pencil, it only uses the maximum context length is just 3,000, which is pretty affordable. And even when the size of the problem is not too large, when the size of problem is just 3 by 3, when there are different categories, there is significant the pencil is also better than chain of thought when varying the context length, meaning that it can use significantly smaller context length to achieve better performance, as shown in this figure, where the x-axis is the maximal context length and the y-axis is the number of parameters. So here are the task time scalability on these 3 different problems, where in this figure, the x-axis is the different inference time budget, and the y-axis is the size of the solvable problem size. As we can see here, using the same model, using the same base model, by enlarging the inference time budget, Pencil can solve significantly larger size problems, more complicated problems compared with chain of thought. So besides of these three examples that we consider here in experiment 3 set QBF and Einstein's puzzle. So how does Pencil perform? Like how about other tasks, more general tasks? Is there any potential that Pencil can solve these other more general problems more efficiently than chain of thought? So next we try to answer a theoretical question of how expressive or how powerful is Pencil. So our result is that Pencil can perform universal space-time efficient computation, meaning that it can solve all problems efficiently. So here is a previous result. The chain of thought is Turing complete, but inefficiently. Here is the result in some previous papers. For any Turing machine, there is this finite size decoder-only transformer such that chain of thought with this transformer simulates the Turing machine with the total number of generated equals to the maximal context length, which is equal to the time complexity for running this algorithm. So here is very simple. The high level idea for proving this is very simple. We can just encode each transition step. Also, the left figure here shows the Turing machine's tape, and the right figure is the like how it can be simulated by using chain of thought. So the right figure is the token sequence. So here the high level idea is like we can encode each transition step, meaning each step of computation of Turing machine as a new token. Here, each new token encodes the state of the current state, the symbol written on the table, and the movement of the head on the Turing machine. So by simulating the Turing machine's run, we can see the number of tokens generated is equal to the time complexity for running that algorithm, how many steps the algorithm it takes to compute to get the final result. We will use how many like the number of tokens is equal to the time complexity for running that algorithm. But the actual, as we can see here, the actual space used by the Turing machine is actually significantly smaller than can be smaller than the number of tokens generated, meaning that it's not efficient simulation of Turing. It's not an efficient way to do the computation. So chain of thought is fundamentally limited in this sense. So how does Pencil address this problem? So this the result for Pencil, meaning that for Turing machine, which uses T steps and S space to compute the Pencil with this transformer computes the same output with the total number of generated tokens proportional to the time complexity and the maximal context length proportional to the actual space complexity for running that algorithm. So for most problems, for most complex problems, the space it uses to address the problem is significantly smaller than the time complexity for solving that problem. Imagine that, like for example, we have like only limited memory for our computers, but we can use this very small memory to run for a very long time and address very complicated problems. So this is like a very general idea in computation. And so the implication for this theory is like Pencil is Turing complete with optimal time and space complexity, and it can solve any computable tasks efficiently. And if we restrict the space for Pencil and the chain of thought, if we restrict the maximal context length, then chain of Pencil can address more complicated problems far beyond what chain of thought can address. So here is an implication. If we only allow the model to have polynomial context length, then the class of problems that can be addressed by Pencil is in P space, and but for chain of thought, it can only solve problems in P. So P here refers to the problem solvable in polynomial time, and the P space here refers to the problem solvable using polynomial space, and regardless of the time. For example, the time complexity for running that algorithm could be exponential or like regardless of how much time it takes to solve that problem. So this is the expressiveness of chain of thought and the Pencil when we restrict the context length to be polynomial bits. The implication of this result meaning that because polynomial is like affordable like memory requirement we use in because otherwise for if the space used is exponential, we don't have such hardware or like computers to store such many information. But like for chain of thought, it can use limited resources using these much resources to do much more test time computes and to address more complicated problems. But the test time scaling for chain of thought is limited by its expressiveness. So here is a general idea how Pencil can solve all problems efficiently. For chain of thought, as we mentioned earlier, it just simulates the computation of Turing machine step by step. One step of computation is equal to one token. But for Pencil, it will iteratively think and summarize, meaning that it will like simulate the Turing machine for a few steps. And when it finds the current space is too large, it will trigger summarization. It will summarize the previous thinking process and only keep the essential part. Here, the step refers to simulating one computation step of Turing machine. And the state here means the current configuration of Turing machine, meaning that the state here is just proportional to the size to the space used in the Turing machine. So by keep thinking and summarize by doing this iteratively, it can keep both the space complexity and the time complexity optimal. So another question is when to do summarize. If we never summarize, if we never erase thoughts, Pencil is just equivalent to chain of thought. the number of tokens generated is the time complexity, and the maximal context length is the time complexity. And another naive strategy is to summarize for every step or for every constant number of steps, which is like similar to like maybe how sliding context window approach do the like if we never erase dots only using sliding window, this is how it works. The number of tokens, though the context maximal context length is proportional to the space complexity, but the number of tokens generated is time complexity times the space complexity, meaning that to keep space efficient, it might sacrifice the time complexity, meaning it will generate more thoughts because every a few constant steps it will trigger summarization. This is the cost that it will take. But for Pencil, what it can do is like it will summarize dynamically, meaning that whenever it finds the current context length is larger than twice the actual space needed, it triggers summarization. It triggers summarization in an adaptive way. So in this way, we can prove that the number of tokens generated and the maximal context length, both of them are optimal. But another question is like, can real-world transformers automatically detect when to do summarization and when to erase the thoughts? And our answer is positive. Here is just a simple proof technique we've developed to prove this result. We've developed a programming language which is called full access sequence processing. So the result here is like any programs written in this programming language, which called FASP, then we can find a corresponding transformer doing exactly the same algorithm as this program describes. So this simplifies the proof. For example, the previous algorithm, we can write this algorithm as we can write a program in FAST to run this algorithm, and because this and so this is just a very simple proof to prove there exists such a transformer can do this automatic summarization process. So here are some like I can walk through the detail very quickly. So here a FAST program just describes a process of constructing the transformers. And for each variable in this program, it represents a transformer architecture, meaning that to compute this variable, to get the value of this variable, we can find a corresponding transformer architecture for running the program up to this line. And for each line of the code, this is just for each line of code, it just takes as input some variables and output another variable. So so what does it mean for transformers? It just takes as input some smaller transformer models and output a more complicated transformer to do much more complicated things. And when the program returns a variable, it returns a transformer, most complicated transformer that can do the entire algorithm. So to summarize, there are some future directions and open questions for example, how to incorporate Pencil into real-world LLM systems. How can we more effectively teach LLMs to reason in a structured way? Maybe, for example, we can consider using some reinforcement learning or supervised fine-tuning on these structured data sets to enable the model to reason in a structured manner to like make them more efficient and address more complicated questions. And does there exist other erasing mechanisms, like, for example, other reduction rules that are even more efficient than Pencil? The reason there is still space to improve is because like the result we prove the theorem is just by simulating the Turing machine, but as we all know, Turing machine is not the optimal computational model. For some algorithms, if we use random access machine to implement it, the complexity is much smaller than using Turing machine to run this algorithm. So maybe there is still some improvement we can make for even make Pencil even more efficient. And are there any other perspectives from which like theories in TCS can help guide practice? And here is the takeaways. In this talk, we propose Pencil, which is a new LLM reasoning paradigm, which iteratively generates and erases thoughts using this very simple reduction rule. And then empirically, we show Pencil is both more effective. It can generate longer and longer thoughts to address more complicated questions using shorter context, and it's much more efficient than chain of thought. And theoretically, we show that Pencil can address any computable problems with optimal time and space complexity. So that's all for this talk. Um, Is there any like questions?
Uh, yes, maybe, I have a question, but maybe I don't completely understand your paper. But my
Mm,
question is that basically it's the savings are purely due some kind of mechanical thing. You split the task into steps, and you don't use unnecessary steps, and that's where the savings come from, right? Not unnecessary steps, but unnecessary data for each follow-up step, right? And but basically the mechanism of thinking doesn't change, right? I mean, I don't know if it's like correct understanding or not. And I've been thinking, what if uh, the model learns some shortcuts, and would it be like, and you just implement the shortcuts, would it be just give you the exponential savings then? Or
so like for example, for the three stats and the QBF problem considered here, there is like so it's commonly known that there is no shortcut to solve these problems. Like every algorithm that can solve it takes at least exponential time to do it. So for Pencil, yeah, you mentioned that Pencil is like teaching it to reason in a structural manner. I think this is exactly what Pencil is doing. Like it teaches the model to reason in such a structured manner, so such that it can both generate thoughts and erase these thoughts. And it wants the model to automatically or like to adaptively determine which part is erasable and which part is not erasable to like find the optimal way to solve this problem more efficiently. I think this is a key idea for Pencil here, and which is um, different from previous approaches, which like just for example provide some prompt templates and like make the model in like reasoning and to teach it for each specific problem to teach it reason in a very like predefined way. I think this is a key difference between our method and the previous method. That
okay,
answers.
so just basically, okay, it seems like I got the crux of the idea, but basically what I'm thinking for future thing, the model could develop some shortcuts that could additionally improve efficiently of reasoning. Alternatively, if you have a body of knowledge of previous, like all the lemma theorems, and you could relate like while reason that some of them are relevant, they efficiently like shortcuts, right? So it would improve, speed up even more, right? Potentially.
Mm,
And you're thinking and you see that you could peruse some previous knowledge, right? Maybe in some kind of body of mathematical knowledge, right? Like
mhm,
that would be that should help even more probably, right? I don't
mhm.
know.
Uh, I'm not sure what the shortcut here specifically refers to because I think it's better like to just to keep the essential information in the context so it will leverage the information more efficiently and more effectively. Like in maybe it will. I think here the shortcut might be a good thing because it means that it can like reason more efficiently rather than just like finding the relevant information among all those irrelevant context. I yeah, that's
Okay. Okay, yeah. Okay, thank you very much. Like a very interesting work. Thank you.
mhm. Thank you.
I think I have one question. It's about because I think that for real world chain of thought there are many cases they are just maybe not recursively, just maybe just generation several subsequently steps. And I think that for each thinking steps, you can just maybe summarize it maybe for one time. So if we face such case that maybe the memory still increase linearly with maybe the thinking steps, yeah,
Yeah,
without.
yeah, exactly. That's how we prove the why pencil is universal is computationally universal with optimal time space complexity. It's just keep summarizing and generating for a certain time and automatically adaptively determine when to do summarize. And there is no recursive here. It's just like keep summarizing and it can still achieve optimal time and space complexity. That's yeah, you are correct.
Yeah, but in this way that I think that it cannot maybe for example just reduce or remove one just maybe wrong step. Yeah, if it's not in a recursive structure, it is in the outermost wise.
Mm, yeah, yeah.
So maybe I think that I'm not sure whether there are some maybe some synthetic task related to this kind, but I guess maybe this kind that it maybe still maybe I guess maybe not optimal ones. Yeah, because that you need to compress something that you need to keep them, not remove them.
Hmm. Yes, I think yeah, you're correct. For most problems, I think you don't necessarily to like find the recursive structures in it. Though I think most like for most problems, you can find the recursive structures here because like there is like hierarchy because like uh, if you consider using some, because most problems, if you consider using some algorithm to do it, you will write some like programs, you will write different functions to do it. Then there is inherently some recursive structures in it because you are calling out another functions and another function calling another function to solve it. So I think it's both optimal. You can write different ways. For example, you don't need to write different functions to implement an algorithm to solve it. You can also, for example, just write a very long different a very long program. You're just using for example a while loop to do it. This is just similar to the idea of doing summarization. There is a while loop, and for when each iteration ends, it will clean the memory somehow. So this is just a different way to solve the problem, and you can use pencil different using different strategy, using different in different ways to solve the problem, like both efficiently. So right.
Yeah, yes, this makes sense. And I
Mhm.
guess another concerning maybe in some real world task here because that you only maybe train pencil on this synthetic task so that I
Mhm.
guess that it can maintain very stable that when it have a very deep recursive level. But I guess
Mhm.
that maybe I'm not sure whether such property that because we know that real world I mean most challenge that you only need maybe at most maybe recursive maybe just 2 or 3 times. Yes,
Mhm.
but I'm not sure that whether if we generalize to real world task, whether it can go such deeper and still keep the stability. Yeah.
Yeah, that makes sense. Actually, for example, if I think it really depends on how complicated the problem is. For example, if we because for most real world tasks, or for most like real world benchmarks, the problems actually are they are not so complicated. We don't need to do like very deep thinking, very like long recursive structure to solve these problems because just because the problem itself is too simple. And maybe we can create more complicated tasks and to test like if it does rely on some like deeper recursion structures and to test if the not using if the model doesn't is not able to erase the thoughts, maybe it's not able to scale to such more complicated problems. But using like by allowing it to erase the thoughts, it can solve these more complicated questions. I think it really depends on like the how complicated the problem is. Maybe we can like manually create um, more like real world questions that requires deep recursive structure to show the benefits of pencil. But you are correct that like most real world data sets there are because they are simple enough that it doesn't rely on very deep like recursive structure, I think.
Yeah, and I guess maybe some reinforcement learning is necessary. Yeah, because I guess the depth ones, the very deep ones, they are mainly just the synthetic ones. Yeah.
Yeah, exactly. I think like combining with reinforcement learning is a very promising future direction if we wanted to think longer and to like explore more like to explore the optimal way to use the to use the erasing capability, then I think reinforcement learning is very important. Yeah.
Yeah, that's correct. Yeah, thank you.
Mhm. Mhm.
Is there more questions? Yeah.
Yes, but I see that you have it in your paper. Maybe I'll look it up. But basically, my question was how FASP relates to RASP, basically.
Oh,
What is?
RASP, you mean?
Mhm.
Oh, so RASP here is like there is the difference between like the FASP and the RASP is like for RASP it doesn't support some operations which is needed to prove this theorem. For example, our proof might rely on some like assumptions about the model architecture. For example, it supports average hard attention, but for RASP the operations allowed there is not comprehensive enough to support proving this theory. When the RASP is first proposed, there is no rigorous proof that like for any RASP program there exists such a transformer architecture that can do this. So we develop another programming language where we can use it to showing the exact connection between the transformer architecture and the programs written in FAST. That's the key difference between FASP and the RASP, right?
Okay, thank you.
Mhm.
Oh, but that part I missed. But it's about hard attention, but in reality you used soft attention, right? In
Oh
your
yeah, exactly. We use assumption that is average heart attention. The model architecture we here is a very small note here. So here is the assumption we use here: finite size and finite parameter precision by infinite precision in forward pass. Also, we assume average heart attention. So for average heart attention, actually we can show that if we allow the temperature to be very small, it can simulate the and soft attention can simulate the average hard attention. So it's a assumption we used here, like a specific architecture, transform architecture we consider in the proof.
okay.
Mhm.
Fine.
There is no more questions. I guess maybe we can end today. Yeah, thank you very
Mhm.
much for
Thank
Chenxiao
you.
talk. Yeah, we will upload the video to the YouTube later. Yeah.
Okay.